You've asked for a pencil?
I hate to be that guy, but I became that guy.
Who are you asking for the pencil?
Usually,
Just
Jake
ever?
is my
Jake's your pencil guy?
Yeah. It was Anakin, and then his, hit the quality kind of went down.
That is awesome. The trade. The pencil trade. Yeah, B schools.
I'm not getting anything in return though. So.
Just got a better quality product.
It's like the tin trade from Mesopotamian days. I don't know where it came from. My dealer won't tell me where he gets it. Okay, so you have a cell, a battery, and this is our Jeffrey cell, and of course the pointy end is the positive, and the other end is the negative. And when we power this up, so this is a couple of plates just made of metal, but they're not touching. So what's going to happen when we turn this on? Yeah, there's going to be a flow of what? Electrons. Which way are they going to flow? Clockwise or counterclockwise? Counterclockwise. So the electrons are going to come out of the negative. Like current is going this way, right? But electrons are actually going that way. So you're going to have a buildup on your plate of, let's do purple, negative charges on one side. And what's going to be on the other side? Positive. Yeah, so you're going to have some positives over here. Not so much because they've moved, but more because they're just left there when the electrons leave, right? So now you have this buildup of charge, and that's handy. It's kind of useful to be able to store and release when we want to. It's not a battery. You're not getting any extra energy. You're just storing the charge so it can be released quickly. And there's lots of good uses for that, which we will get into. So there's a distance between the plates. Now, the distance is important because something happens here. The cell is pushing the charge, right? But there's another force happening. What other force is happening? Yeah, that's right, Ben. You get an electrostatic force between the plates just because they become oppositely charged. And so the electrons are pushed around the circle, but then when they start to build up here, this becomes positive, and so they actually are being pulled by the other plate as well. We'll talk about the functions involved there. So, capacitance is C, and C is the amount of charge that will be stored on the plate per volt of energy supplied by the circuit. Yeah. So the amount of charge built up on the plate, Q, per voltage supplied by the circuit. So maybe we can label those. Purple. Now you might have a question of, well, which plate do you count? Yeah, and so you count both. What would you say about the charge on each plate? Yeah, equal and opposite, right? So if your Q is, I don't know, 4 times 10 to the 8 coulombs, then that's going to be negative on the one plate, and it's going to be positive on the other plate. And they're always the same. This voltage is the voltage supplied by the circuit. This kind of happens in different ways, but I'm just going to say supplied by the circuit. So it's just the voltage that's pushing the charge onto the plate. And then of course we can change that into Q. If you want to find the charge on the plate, what would that be? Yeah, Q equals CB.
Is the battery the one that's supplying the voltage?
Yes. Yeah. What happens if we just have two plates with no cell in the circuit?
It's just metal plates.
Nothing. It's just a couple of plates, and they're just now. What if we did this, and then we had? I should have drawn it in, but what if we had a switch in here, so that I turn it on, and then I open the switch, and then I turn it off?
There'll be
What's gonna
discharge.
happen?
That's gonna.
Are the plates gonna be able to go back to neutral? No, they're gonna be stuck there, right? There's not gonna be a way for these electrons to run back around. So you can have charge build up. If you push it in there, you can store it there just by opening the circuit, and you can keep it there for a bit. Okay, and then what happens if I close the switch, even if the cell is off? It'll just run back, right? This is handy to be able to do in a circuit as well, because you can store a charge if you have a voltage for a short time, and then you can release the charge when you want to do so. Okay. So if you have these two formulae, what does that tell you about the relationship between charge buildup and voltage supplied? Inverse?
Well, the more voltage you have, the less capacitance.
I don't think it's inverse.
Because the capacitance stays the same.
Oh, no, it's the first one.
Right, so voltage and capacitance are inverse, you're right about that. What about the charge buildup and the voltage? It's directly proportional, right? So what happens if I double my voltage? Then you double the charge built up, right? By the way, we should review this probably. What is charge? Coulombs, good. Borna, what's a coulomb? Okay, it's a good thing we're doing. Borna just went through. He was like, don't know. Sana, what's a coulomb? Say that again.
Electrical force between.
No. B, what's a coulomb?
It's a truck. It's a truck.
Isn't it just
Who said it's a truck? Okay, Ben's right, it's a truck.
It's just a number of electrons.
What is a truck? Jake, say that again.
It's just a number of electrons.
A coulomb is a certain number of electrons. That's all it is. We think of them as little trucks driving around the circuit, right? How many coulombs, or how many electrons are in a coulomb?
Something times 10
With 6 times
1.6 times 10 to the negative 19 is the number of coulombs of charge on one electron, right? So if you do 1.6 times 10 to the negative 19 and you inverse it, I think it's 6.28 times 10 to the 18. Can someone do it for me?
Yeah, it is
I don't trust us.
I remember.
Yeah? 1.6, negative 19. 6.25 times 10 to the 18. It might be 2.8 with more decimals, I don't know. So maybe I did have it right. But so this is the number of electrons in one coulomb. Why did we choose to use that number of electrons for a coulomb? Because when we made this stuff up, we didn't know about electrons. We didn't know what they were. We just called a piece of current 1 amp. Right, so 1 ampere of current is what you get when you apply 1.
Per time.
Right. 1 volt of electromotive force produced 1 amp of current if you have 1 ohm of resistance. And so then we had to work out, when we found out, oh, these are electrons moving around, then we had to work out how many electrons were in 1 coulomb. So you just think of it as a container, a truck of electrons going around. Okay, so if we double our voltage, we get double the charge on the plate. And what would you say about this number, this C? That is measured in farads, by the way. I guess I should do an arrow for that one too. We call this capacitance in farads. And the prefix is very wildly, as Kenta found out when he was using these things. You can go microfarads and picofarads and all kinds of crazy prefixes. So 1 farad would be 1 coulomb per volt, I guess. In the real world, what determines the farads? What determines the capacitance?
Dielectric.
The what?
The explanation of the structure of the.
Yeah, you're both right. So Kent is talking about dielectrics, which we will get into in a second. It's determined by the structure, the actual physical structure of the capacitor. So in other words, if you can change your voltage and everything, it's not going to change the capacitance. It's just that if you push more charge, you get more charge. If you push more voltage, you squish more charge onto those plates. And what do you think would? How would we? Let's say we build a capacitor, and then we want a bigger one. Like we want to store more charge. How would you do it?
Something in
Be just like this. If you make the plates bigger, you just have more space to store more charge, right? So the bigger the plate, the more charge. And Kenta, what did you say?
put something in between, put a dielectric in between.
So if you make this distance closer, what happens then? Eric's nodding his head.
Just looking down the notes.
He's looking at the notes.
Lower capacity.
Not lower.
If you put it together.
If you put them together, are you gonna get more charge or less charge?
Nice. More. If you put it together.
Yeah.
It's less.
So hold your
Is it
hands
just
like
like-
this. Imagine you have a 1.5 volt little AA battery pushing charge onto these plates, right? And you have, your fingers are tingly because you've got some charge on there, just like with the Van de Graaff generator. What's happening with the electrons on this hand? Shake one hand, this is your electrons. The other hand is your protons. What's happening between these two?
Attraction.
They're being attracted, right? If I move them closer, and everything else stays the same, what happens to the attraction here? Increases, right? Stronger force. So more electrons are going to be pulled around and squished on the plates. The closer you can get it, the more electrons are going to be pulled onto that plate. And it increases when you get really close. So the part of the reason for a dielectric, and what a dielectric basically is we spray paint this with some stuff. So you kind of like, this is supposed to come later, but you kind of like, you spray some coating on this, and then you just smack them together. And the coating is the only thing between the two plates. So you get a really, really short distance. And as Kent says, the dielectric can actually, because the permittivity of some materials is less than others, and some materials have a lower permittivity than vacuum, you can actually have more charge built up. The attraction is greater. And there's a bunch of stuff to go with that. So, and what we do is we get them right close together, spray the coating, get right close together, and then because we don't want to have this big plate in the middle of our circuit, we roll them up. And that's why a capacitor looks like a disc. If it's a disc, it's just two little disc plates stuck together. But if it's a cylinder, it's like this. If you have your two plates and they're like, this is gonna be hard to draw. Should not have done this. But I'm there now. This one goes. I don't know if that makes any sense, but you roll them up and then you put them in this kind of like a, you know those desserts that are like cake and cream and they roll them up?
Cinnamon roll?
Yeah, sure. Yeah, something's kind of like that. And so you'll see and if you see a made one, it kind of looks like this, and it'll have some like 2 picofarads or something like that. And on the top, there will be this metal. It will be coated, and the 2 prongs come out the bottom. And this plus, Kenta, what is that for?
Where?
On the top of the capacitor.
It's so when you blow it up, it explodes.
Yeah, it's literally, it doesn't mean positive. It's like a crease in the metal, so that when the capacitor gets too hot and it melts itself together, the top will go pop, like a popcorn popper thing, and it lets you know that this capacitor's dead. You need to replace it.
If you, sorry, I'm going back a little bit, but
Go
if you
ahead.
put the plates closer together and the electrostatic force is stronger,
Yeah.
doesn't that mean that it needs less force to bridge the gap?
Yeah.
Start flowing. But doesn't that mean you
But
end
the
up with
force
less-
is the same. So what's gonna happen? Where's the force coming from?
It's electrostatic from the.
There is electrostatic force, but what's pushing the charge onto the plates?
Oh, from the cell.
Right, and is that voltage changing?
No.
No. So that's why you get the extra movement. Oh, no cream. Just one cream. Borna, get me some cream. He's on a call somewhere. Does that make sense, kind of, sort of? It's kind of a weird thing, but so here's the formula. You guys think in formula, so maybe this will help. Another formula for capacitance is this guy. That's the permittivity of free space. And you can multiply that by the area of the plates divided by the distance between the plates. I always look for my phone in my pocket while I'm filming myself. Listen, how long has this been going?
Most 20 minutes.
Okay, I'm gonna. That's part 1.